Good morning, ladies and gentlemen. We're going to do 8.7. We're going to be talking about the indeterminate forms and Wattles Rule. So last year we learned what constituted an indeterminate form, but now we're going to just review that, and then we're going to talk about using Wattles Rule to evaluate a limit. So remember that the indeterminate form, when you're doing these types of problems, before you get to do cool stuff, you have to show that the indeterminate form exists. So the indeterminate form happens when I try to take the limit of a function as x approaches infinity, and when I do, I might get 0 over 0 or infinity over infinity, and you could do any combination. So the indeterminate form exists when this happens. So remember that we have to eliminate the indeterminate form. And sometimes that's fairly simple. And you can go back and review the way that we've done this in the past. I can do it by factoring. Sometimes I can multiply by a conjugate. Sometimes I can get creative. But sometimes the functions are just annoying and really hard to eliminate that indeterminate form. And so instead, we use this cool thing called Wattles Rule. And I know it looks like it's spelled L Hospital's Rule. That's for us rednecks. But it's Wattles Rule. I think it sounds cool. Wish I had abilities to speak other languages. So then what this says, if I'm trying to take the limit of a rational function, or maybe even as x approaches c, it doesn't have to necessarily be infinity. So let's say I'm trying to take the limit of a rational function, and I run into the indeterminate form. Once I show the indeterminate form exists, then I can do Wattles Rule. And so the way that it works is I just take the derivative of the top, and I take the derivative of the bottom, and then I attempt to do direct substitution. And then if it doesn't work, then maybe I do it again. So you might have to repeat Wattles Rule a few times. Typically, it's only a couple of times, but you could potentially do it more depending on how complicated your rational function is. But you continue until you get rid of the indeterminate form, and then you can do your direct substitution to solve. Another way to think about Wattles Rule is that it is an extended mean value theorem. Remember, the original mean value theorem is that the derivative is equal to f of b minus f of a over b minus a. That's the original mean value theorem. But if I extend it, since I have a derivative divided by a derivative, these guys go away. And so then I would end up with f of b minus f of a over g of b minus g of a. And because the denominators are the same, then they would cancel because I have fractions divided by fractions. All right, so Wattles Rule is glorious. It makes life so much easier when we're trying to get rid of that pesky indeterminate form. So let's just start by doing a couple of examples. And you really only have, how many examples do I have? 1, 2, 3, and that's it. The second one is kind of interesting, so I'm just going to do, actually I think I'll take one out and make us even shorter today. So for this example, I want to take the limit as x approaches 0 of e to the 2x minus 1 over x. Well, if I do my direct substitution, I get e to the negative 1 over 0, oh no, and so I end up with 0 over 0, which is the indeterminate form. So therefore, I'm going to use Wattles Rule. So I still have to manage and carry my limit notation, but if I take the derivative of this, this is going to be e to the 2x minus 1 times the derivative of the top, which is 2, okay, and then I have my derivative of the bottom, which is 1, okay. So then when I do rewrite this, this is the limit as x approaches 0 of 2 times e to the 2x minus 1 over 1. Well, notice I got rid of the variable in the denominator, so now when I do my direct substitution, I'm not going to get the indeterminate form. So now I can do my direct substitution, and I get e to the 0, which is 2 times 1, which is 2. Well, that was pretty doggone easy, so now I can say that the limit of f of x divided by g of x as x approaches 0 is 2. And remember, we always want to report our answers well. So the next example is a little bit entertaining, not too crazy, but it is kind of a unique situation, and I want to show that to you. So this is the limit as x approaches infinity of 1 plus 1 over x raised to the x, okay? So on this one, remember as x approaches infinity, this is going to approach the horizontal asymptote 0, but when I substitute direct substitution, I get 1 plus 0 raised to the infinity, which is 1 to the infinity, which is the indeterminate form. Okay, so that's just a little bit weird. All right, so we're going to do this problem a little bit differently. So we're going to write down an assumption. So we are going to assume, and if you're going to do an assumption, you have to write it down because that's kind of part of your work. So we're going to assume that the limit exists and is equal to y. So I'm just going to call the limit a variable. So I'm going to write y is equal to the limit as x approaches infinity of 1 plus 1 over x raised to the x. So then because I have a variable in the exponent position, I'm going to take the natural log of both sides. All right, so I'm going to say the natural log of y is equal to the natural log, does not look weird, of the limit as x approaches infinity, and then I have my 1 plus 1 over x to the x, okay? Then I can rewrite this because the exponent goes out front, so this is x times the, I'm actually going to rearrange a little bit. So before I do that, let me scribble that out. I'm going to pull the limit out, so I'm going to make him the limit as x approaches infinity of x natural log 1 plus 1 over x, okay? So that would be how I rearrange it, okay? And the only reason that we can do this is because the function is continuous, so we get to write this, okay? So now what I'm going to do, and this is where I think it's a little bit of a stretch, is I'm going to write that the natural log of y is equal to the limit as x approaches infinity, and then this is going to become the natural log of 1 plus 1 over x, and then I'm going to divide it by 1 over x, and we're going to say that that equals 0. So let me explain where this came from. Right here, I had an x, but if I rewrite it as 1 over x, it's the same thing, but this is going to, sorry, I forgot a 0, create my indeterminate form, because as x approaches infinity, this is going to approach the horizontal asymptote. This is going to approach the horizontal asymptote, so I still have the indeterminate form, okay? So now what I'm going to do is I'm going to manage this inside, okay? So I'm going to take my derivatives using Wattles Rule. So then if I take the derivative, all right, so I'm going to get, I'm not going to do this side yet, so I'm just going to leave him alone. So I'm going to circle him so I don't forget to do that. And I'm going to take the derivative of this side with Wattles Rule. So I'm going to write the limit as x approaches infinity. When I take the derivative of this, I get 1 over 1 plus 1 over x times the derivative of the inside, which is x to the negative 1. So this is going to be 1 over a negative 1 over x squared. And then if I take the derivative of the denominator, I'm going to get a negative 1 over x squared. Okay, so that was the derivative of the numerator, the derivative of the denominator. These factors are the same, so they cancel. Well, now I've just eliminated my, oops, I forgot the arrow. I've just eliminated my indeterminate form because as I take the limit as x approaches infinity, this guy goes to 0, so I get 1 over 1, so the limit is 1. but I still have this equation, the natural log of y is equal to 1. So I'm still not quite done because remember in the very beginning we said that the limit existed and was equal to y. So that means I still have to solve this for y to find the limit. So I go back to exponent form, e to the 1 is equal to y, so y is e. So then as I write my conclusion statement, and this is the limit, not this, so then I would write the limit of f of x as x approaches infinity is going to be e. So that's the reason I wanted to do this particular example, because it is a little bit entertaining. Alrighty, that is it for the day. Lucky dogs, nice short video, and I will see you tomorrow.